Okay. Hello everyone, very good evening. I welcome you all at India's most comprehensive preparation platform for all competitive exams. And you all know this is the second part of the previous year question discussion of the IISc Bangalore for the subject Computer Organization and Architecture. So, what are the different topics which I am going to include in this particular session? So, please. Yesterday we discussed only the basics of computer organization architecture and the questions related to machine instruction, addressing mode and control unit design. Today we discuss the questions of instruction pipelining, memory organization and DMA. So there will be only two questions from DMA and IO interface, but there are 19 questions. Please mark this number. There are 19 questions from the topic of instruction pipelining and memory organization. So 19 questions are asked, including 2002, 2008 and 2016. So I hope you can understand the weightage of these two topics, instruction pipeline and memory organization in computer organization and architecture. So we'll discuss them one by one, but you all know that there will be 21 questions. So I'll be a little faster. If you guys are facing any difficulty in any particular question, please let me know. So this is the brief introduction of myself. My name is Vishal Rawatia. I have 10 plus years of teaching experience. Following are the achievements and areas of expertise. So the performance of pipeline processor suffers if the pipeline stages have different delays. Yes, if the pipeline stages, let's assume that let's assume it's a 4-stage pipeline, right? So let's assume that the time for this is 1 millisecond, time for this is 2 millisecond, time for this particular stage is 3 millisecond, time for this is also 2 millisecond. So you know that we will have to consider the cycle time of pipeline processor as max of this, which will be 3. So ultimately in each stage we will stay for one clock cycle, that is for 3 milliseconds. So you will eventually waste 2 milliseconds in this particular stage, you will waste 1 millisecond in this stage, you will waste 1 millisecond in this stage, and in this stage there will be no time wastage. So basically, if the stage delays of the different pipelines are different stages of the pipeline are different, then the stages with the less delay compared to the maximum delay will eventually waste some time, and ultimately, yes, it will suffer. The pipeline will suffer from with respect to performance. Let's assume something else. Consecutive instructions are dependent on each other. Yes, it will correspond to data hazards, and because of data hazard, there will be stall cycles present in the pipeline. That is again the wastage. The pipeline stages share hardware resources. It will be known as structure dependency or resource conflict. So if the resource conflict exists, then also these stalls will be present in the pipeline. So all three will correspond to degradation of performance. Clear? Next is let's understand the next question. Okay, so a non-pipelined single cycle processor operating non-pipeline. So it's a non-pipeline processor. Single cycle processor means that one instruction can be executed in one cycle. One instruction execute in one cycle. Good enough. So students may get confused because of this particular statement, that what do I mean, or what do they mean by single cycle processor. Single cycle processor means all the instructions of that particular processor can be executed in one clock cycle time, operating at 100 megahertz. So when it is 100 megahertz, then time period, that is the cycle time for this non-pipeline processor, will be T equals to 1 by F, that is 1 upon 100 megahertz. What will it be? Yes. So 1 upon 100 megahertz, that is 10 raised power minus 8. So this 2 and this 6, 10 raised power minus 8 second. I can actually call it as 10 microsecond. Whatever. Oh, sorry. 10 nanosecond. right? Multiply by 10, divide by 10, minus 9, yeah, 10 nanosecond. Clear? Good enough. Let's assume converted into synchronous pipeline processor. So it's a synchronous pipeline processor in which the decisions will be taken by a clock cycle. Therefore, each stage needs to complete its task within the clock cycle with 5 stages, this, and this respectively. The delay of the latch is 0.5 nanosecond. Okay. So this is the scenario. What will be the cycle time of the pipeline processor? This is the cycle time for non-pipeline processor. What will be the cycle time for pipeline processor? So it will be the maximum of 5, 2.5, 1.5, 2, 1.5 and 2.5. So it will be the maximum of 5 plus the buffer delay or latch delay, that is 0.5. So it will be 3 nanosecond. 3 nanosecond. Right? Now it is asking for the speed up of the pipeline processor for a large number of instructions. So by default, the speed up is defined as n into tn divided by k plus n minus 1 into tp. Yes, sir. But when n is very large, it degenerates into tn by tp. It degenerates into tn by tp. So for large number of instructions, it is asking, therefore it will be tn by tp. The value of tn is 10 nanosecond. And the value of TP is 3 nanosecond. So 10 by 3 is 3.33 basically. So the correct answer is option B, option C. Clear? Let's move to the next question. Delayed branching. What is the concept of delayed branching? It says that if the branch instructions are there, then because of branch instruction, branch may be taken, may not be taken. So the next slot for the instruction after the branch instruction is defined as delayed slot. Right? Now, generally, there are different methods, but when we talk about delayed slot scheduling, then in the delayed slot, we can schedule the instruction from 3 different places. That is, first one is the instruction before the branch instruction. There are 3 approaches. Instruction before the branch instruction. When can we use this? When the branch condition does not depend on the output of the previous instruction. Another is instruction from target address, and third one is instruction from fall through. So when we talk about scheduling, in that particular slot which is after the branch instruction is known as delayed slot scheduling. We can use one of these 3 approaches. The best one will be this first one, but it can be used only when the condition of the branch instruction does not depend upon the previous instruction. Simple concept. So let's look at this. So delayed branching can help in handling the control hazard. Yes, if you are eventually inserting a correct instruction, then you will not have to flush the pipeline and you will not face any stall cycle in that particular case. The following code is run on a pipeline processor with 1 branch delay slot. 1 branch delay slot means, why 1 branch delay slot? Because the outcome of the branch instruction will be available at the end of second cycle. So if the outcome of the branch instruction is available at the mth cycle, then the number of delayed slot will be m-1. Number of delayed slot will be m-1. So if it is saying 1 branch delay slot, it means that the output of branch instruction will be available at the end of second cycle. That's okay. So that's okay. So these are the 4 instructions, I1, I2, I3, I4, and this is the branch instruction. Now it is asking, so this is the branch instruction, the slot for the next instruction after this branch instruction is defined as delayed slot. So this is your delay slot. This is your delay slot. Now it is asking which of the instructions I1, I2, I3 or I4 can legitimately occupy this delay slot without any other program modification. So let's first of all, let's check whether the instruction before the branch instruction is independent of the branch condition or not. So let's look at this. This is the instruction I4. This is your instruction I4. It reads the value of register R1. It reads the value of register R1, and based on that, it stores the content of memory location of the address provided by register R4. So what is going to change? The content of memory location is going to change because of the execution of instruction I4, whereas the branch condition depends upon the content of register R1. So please try to understand that because of execution of instruction I4, the content of register R1 is not going to change. It means The branch condition does not depend upon the output of the previous instruction. Therefore, this instruction I4 can legitimately occupy this delay slot. So the correct answer will be instruction I4. Correct answer will be instruction I4. We'll discuss all these things in detail when we'll understand the concept of COA, but please, we are discussing the previous year question. If you guys are having any difficulty, you can ask. Now, next one, same concept. Those two are the questions of the same year, one after another. So, delayed branching can help in handling the control hazards, right? That's what we said. The delayed branching can actually help in handling the control hazards. That is, the stall cycles which you will observe because of the execution of control or because of the control transfer instruction may be reduced if you use the concept of delayed branching. Now, for all delayed conditional branch instruction, delayed conditional branch instruction, conditions, so if they are conditional, then condition may be true, condition may be false, we don't know. So, irrespective of whether the condition evaluates true or false, irrespective of whether the condition evaluates true or false, what's the idea? It says that the instruction following the conditional branch instruction in the memory is executed. We'll talk about this. Okay. Now, the first instruction in the fall through path is executed. Please try to understand that fall through path will be the original program, and when we load the program into the memory, this program will be loaded into the memory after the compilation. That's very important. People do not understand this. Program will be loaded into the memory after the compilation, and this concept of delayed branching is implemented with the help of by compiler. So compiler is intelligent enough. Compiler is intelligent enough so that it can identify that whether I can place the instruction in the delay slot from the target address or from the fall through sequence, or we can place the instruction before the branch instruction in the delay slot. So the compiler will identify this. So when you are loading the program into the memory, compiler has already taken the decision that which particular instruction should be placed in the delay slot, and then it will be loaded into the memory. So all the tasks has been performed previously. So to whichever instruction is available after the branch instruction in the memory, that particular instruction will be executed based on the incremented program counter value. It says the first instruction in the fall through path is executed. It may or may not be correct. Why? Because if the instruction from the fall through path can be placed in the delay slot, then only that will be executed. It may be possible that we have placed an instruction before the branch instruction into the delay slot, so this will become wrong. So it's saying irrespective whether the condition evaluates to true or false, what will happen? Now, the first instruction in the taken path is executed. Taken path means the instruction from the target address. So neither it is not guaranteed that the instruction will be taken from the fall through sequence. It is not guaranteed that the instruction will be taken from the target address. The branch takes longer to execute than other instruction. It's absolutely rubbish. There is nothing like that branch will take more time. All the instructions will take equal amount of time if it's a cycle, if it is a pipeline, and in general average number of cycles per instruction will be 1 if there is no stall cycle. So it's obviously wrong. So the only thing is the instruction following the conditional branch instruction in the memory, because when it is being loaded into the memory, the compiler has taken the decision that which particular instruction should execute irrespective of the condition evaluates as true or false. Okay, Rohit. Okay. Right? So that's the idea. So the correct answer for this will be option A. I have told you, Rohit, if you guys are facing any type of difficulty, please let me know. But otherwise, there are 21 questions from this 3 years and only 2 are from the DMA. But obviously, if you are not able to understand, then we will go slow. These 2 questions were absolutely easy, I believe. 3 is comparatively, 3 and 4 are related to the same concept, that we can either place the instruction which is before the branch instruction or from the fall through sequence or from the target address. So the same concept is being used in this particular question number 4, that is which one is placed in the delay slot? It has been decided at the compile time itself, and then only the program is loaded into the memory. So no matter whether the condition evaluates it's true or false, whatever instruction is available in the memory after the branch instruction, that will execute. Okay. Next, this is very easy. Which of the following are not true? Which of the following are not true in a pipeline processor? It says bypassing. Bypassing means if you guys don't know the another name, then you must know it by the name operand forwarding. Operand forwarding or bypassing is the same thing. So it says operand forwarding can handle all read after write hazards. Is it true or false? Is it true or false? So if you guys were discussing this concept of operand forwarding, then in general you will visualize that all the read after write hazards can be eliminated using operand forwarding, but there is a specific case. In that particular case, operand forwarding will not be able to eliminate the stall cycles present in the pipeline because of raw hazard completely, right? And that will happen because of load type of instruction. So if I say load R0 and some memory location 200, if this is the instruction, and if the next instruction is something like add R1, R0, R2. So this addition instruction actually needs the content of register R0, but this content of register R0 will not be evaluated in the execution stage. It will be available after the memory access. So generally what do we do? That in the decoding stage, we will try to provide the content to this instruction addition from the output of execution stage, but this content of register R0 is not being evaluated by execution stage. Therefore, in the next stage itself, even if we use concept of operand forwarding, we will not be able to provide the content of register R0 to this instruction addition. Therefore, bypassing can handle all raw hazards? No. No, no, no. If the instruction is the load instruction and the next instruction uses the content loaded by that load instruction, then obviously your operand forwarding will not be able to solve this particular problem. Next one is register renaming can eliminate all register carried right after read hazards. It will be able to eliminate all right after read hazard as well as right after write hazard. You know that we use a thing called reorder buffer. When we say register renaming, then we rename the buffer and we store the result in the reorder buffer temporarily until the out of order sequence instruction is executed. When that particular instruction is executed, we will store the corresponding values in the dedicated register from the reorder buffer, and we will be able to eliminate all the hazards. So register renaming can eliminate all register carried right after read hazard. It is true. This is true. This one is false. So it is asking for not true. It is asking for not true. So yes, obviously first one is not true, but second one is true. Then the next one is control hazard penalties can be eliminated by dynamic branch prediction. Can be eliminated. No sir, they can be reduced. Because it is just a prediction. It is just a prediction. It may be true or it may be correct. Your prediction may be correct. Your prediction may be wrong. If your prediction is correct, then you will be able to eliminate those stall cycles. But whenever your prediction is wrong, you will eventually encounter some of these stall cycles. So when it says that it can be eliminated, no, it cannot be eliminated. They can be reduced. They cannot be eliminated completely. They can be reduced. So this statement is also false. So second one is true, 1 and 3 are false. So which of the following are not true in the pipeline processor? 1 and 3 are not true. You need to understand the terminology. It is saying eliminated or can handle all. So not all. cannot be eliminated, can be reduced. Clear? Next, question number 6. Okay, so this is again a very simple question related to concept of pipeline. Consider a 3 gigahertz processor. So if okay, 3 gigahertz processor with 3-stage pipelines, with a 3-stage pipeline, and stage latencies are T1, T2 and T3. So please try to understand that there are 3 stages in the pipeline: S1, S2, S3. And the stage latencies, that is S1 will take T1 amount of time to complete its task, stage S2 will take T2 amount of time to complete its task, and stage S3 will take T3 amount of time to complete its task. Now the values are available, that whatever the relation between T1 and T2 and T3 is available, if the longest pipeline stage is split, longest pipeline stage is split into 2 pipeline stages of equal latency. So please, first of all, let us try to calculate the values. First of all, let us try to calculate these values, that what will be the values of T1, T2 and T3, right? So, sir, we know that the frequency of the processor is 3 gigahertz. That is, clock cycle time T equals to 1 by f. T will be equals to 1 by f. Clock cycle time will be equals to 1 by f. Fine enough. Now, it is asking that, sir, the value of T1 is 3 T2 by 4 and value of T3 will be T1. Okay. I hope these values are correct. I am not doing anything wrong. T1 equals to 3 T2 by 4. So it's basically nothing but 3 by 4 T2. It is 3 by 4 T2. It is T2. And here it is T1. Or basically you can say 3 T2 by 4 is actually 2 T3. 2 T3. So what will be the value of T3? The value of T3 will eventually become 3 by 8 T2. Value of T3 will become 3 by 8 T2. Clear? So you can actually see this 3 by 4 is less than 1. This 3 by 8 is also less than 1. And this T2 is the maximum. This T2 is the maximum. So once you know that this T2 is the maximum value, just 1 minute. I lost your connection. Yeah. When if you know that this T2 is the maximum value, then this 1 upon 3 gigahertz will be with respect to this T2, because we know that TP, or the cycle time of the pipeline processor, is max of stage delay. Max of stage delay. So when we know that the value among T1, T2 and T3, the maximum value is T2, therefore this TP will be equals to T2 and this T2 will eventually be equals to 1 by f. T2 will be equals to 1 by f. Now it is saying that if the longest pipeline stage is split into 2 pipeline stages, it is split into 2 pipeline stages. So S2 will eventually get split into 2 stages. Let's say S2 dash and S2 double dash. S2 dash and S2 double dash. The time for this will be T2 by 2 and time for this will also be T2 by 2. Why? Because 2 pipeline stages of equal latencies. That is, earlier we used to perform the task of stage S2 in T2 time. Now we are dividing into 2 parts, so each one of them will take half of amount of time. The new frequency is how much? New frequency is how much? So please, when we say that the new pipeline is S1, S2 dash, S3 dash and S2 double dash and S3, then we need to define that what is the maximum value. What is the maximum value? This time you know this is T2 by 2, this is T2 by 2, this is 3 by 8 and this is 3 by 4. So among 3 by 4 T2, 1 by 2 T2, 1 by 2 T2 and 3 by 2 T2, the maximum value will be this. Max for new pipeline. This is the maximum for new pipeline. So for new pipeline, this will become cycle time of pipeline processor, of new pipeline processor. So TP new will be nothing but 1 upon F new. Whatever the new frequency is, TP new will be T equals to 1 by F, that will remain same. So TP new will be nothing but 1 upon F new. Now what is TP new? TP new is 3 by 4 T2. TP new is 3 upon 4 T2. This will be equals to 1 upon F new. Right? Now let's look at this. Sir, the value of T2 is actually nothing but 1 upon F, that is 1 upon 3 gigahertz. So I can actually write it as 3 by T2, and value of T2 is 1 upon 3 gigahertz. This is actually equals to 1 upon F new. Right? So this, this is 3 by 4. This 3 by 4. This 4 will be same. So 3 cancels out. So you know that from here F new will come out as 4 gigahertz. F new will come out as 4 gigahertz. So the concept is quite simple, that first we need to define the cycle time of the processor based on the original frequency. Now, when you have divided the stage with the longest delay into two equal parts, it may be possible that the cycle time of the new pipeline will change, and we can eventually observe that earlier the cycle time of the pipeline processor was T2, and the cycle time for the new pipeline after dividing the stage into two stages becomes 3 by 4 T2. So now frequency will be defined with respect to this new clock cycle time. Earlier the frequency was based on T2. So here the answer will be 4 gigahertz. Clear? Let's move to the next question, question number 7. So it's a different type of question, not actually related to concept of pipeline, but this is actually a question which is related to the understanding of the execution. So please, let's look at this. Suppose the functions f and g can be computed in 5 and 3 nanoseconds by the functional unit uf and ug respectively. So there are two types of function, one is f, another is g. To evaluate function f, you will use the unit uf. To evaluate function g, you will use the unit ug. Okay, whatever. Given two instances of uf, now it is again being said that in your machine you have two copies of functional unit f and two copies of functional unit g, right? It is required to implement. Now, two instances means these two units can perform the operation parallelly. What will be lengthy for exam? Manasvi, what will be lengthy for exam? Well, this process you are asking that this will be lengthy for exam? Yeah, I do believe that. I'm not writing, I'm actually writing each and everything here. So I'm also trying to give you the understanding that how the question will be solved. Otherwise, this question can be solved in 1.5 minutes. And I believe that for the gate questions, few questions will require only 1 minute and few questions may require up to 10 minutes. So in the very first go, you must understand that what are the questions which will take more amount of time. Skip those questions for the time being. First of all, try to solve the questions which will take 1 to 3 minutes. First of all, try to solve the questions which will take 1 to 3 minutes, and in the second round, choose the questions which you will be able to solve, but those questions are going to take more amount of time. So that's, therefore we say that there are 2 rounds are needed when you are appearing for the GATE exam. 2 rounds will be needed when you are appearing for the GATE exam. One is in the first round, you will identify the questions which are requiring less amount of time. You will solve those questions then and there. You will solve those questions then and there. And when you realize that, okay, this type of question is going to take more amount of time, eventually you will just mark it for, you will just mark that particular question for review. And in the second round, you will eventually try to solve all those questions. So there's a strategy, and that's very important. Clear? So it's not so that all the questions of the GATE exam can be solved in 1 to 3 minutes. Yes, there will be questions which will take up to 8 to 10 minutes. Up to 10 minutes. And ultimately, you may say, sir, what if we skip those questions? If you are done with all those questions which will require 1 to 3 minutes in the very first half of the examination, in the second half, you will have to go for those questions which are taking more amount of time. Obviously, there are only 65 questions. I mean, this strategy is quite simple if you actually believe. There are 65 questions. Out of those 65 questions, I get not more than 20 will require 20 questions. Let's assume 20 questions will require more than 5 minutes. 20 questions will require more than 5 minutes. Then I can say remaining 20 questions will require the time from 2.5 to 5 minutes. And there will be 25 questions which can be solved in less than 2.5 minutes. And that's in general is true. That's a general understanding. I should not go into this particular detail in this video, but as you have asked, let me tell you that this will be the scenario. So first of all, try to complete these questions as fast as possible. So 25 questions, if each one requires 2.5 minutes, then it will take less than 1 hour. It will take less than 1 hour. Then for 1 hour, you will be able to solve these questions. And for last 1 hour, you will be able to solve up to 10 questions from this particular topic. So I know that you are not going to solve all 65 questions. Your target will be 55 to 60 questions. Your target will be 55 to 60 questions, and that's how this time will work. So that's a different story. We should do it some other time, not in this video. Yeah, but this question is lengthy. The question we are talking about at this point of time. If you have identified the trick, it can be solved easily, but in order to explain the concept, I will require more amount of time. And in this session itself, I'll discuss a question which may take up to half an hour, but the problem is, while explaining that question, it may take up to half hour. While you will solve those 3 questions, the very first question will take more than 10 minutes or about 10 minutes. And the remaining 2 are dependent on that. So they can be solved easily. So anyway, so there are 2 units. One is unit F. Now I'm saying that there are 2 units which are capable of performing function F, and there are 2 units which are capable of performing the function G. Good enough, sir. Now, for this type of unit, you require, the computation of function F will take 5 nanosecond, and the computation of function G will take 3 nanosecond. Now, that's okay. Given two instances of this, it is required to implement the computation of this particular function. So, you actually need to evaluate f of G of x1. So, for I varying from 1 to 10, so you need to evaluate f of G of x1, you need to evaluate f of G of x2, you need to evaluate f of G of x3. So, these are all the values which you need to evaluate. Now, the good understanding is that first you will have to perform the function G, because if you have not performed the function G, you will not be able to compute this function f, because f is being applied on the output of function G. F is being applied on the output of function G. So what will happen? So please. There are two units G. So you can simultaneously start performing the operation on 1 and 2. So this will eventually give you G of x1, and this will eventually give you G of x2. Now, if you start at time 0, the function unit G will produce its output at time unit 3. Therefore, at time unit 3, you will have, so please, at this point of time, function unit F will be idle. At this point of time, function unit F will be idle, because until you have the value of G1 or G of x1, G of x2, G of x3, etc., you cannot calculate F of G of x1, F of G of x2, and so on. So this will remain idle. Now, at time unit 3, you have the value of x1 and x2, G of x1 and G of x2. Therefore, you will start performing F of G of x1, and at the same time, you will start performing F of G of x2. Now, it will start at time unit 3. It will start at time unit 3 when function unit G has performed these two operations. Then it will take how much time, sir? It will take eventually 5 minutes of time. For the evaluation of function F, you take 5 minutes of time. So from 3 to 8, you will get the values of f of g of x1 and f of g of x2. In the meanwhile, what will happen? This function unit UG will keep performing its operation. So by the time the function unit f is performing the operation on g of x1 and g of x2, the function unit f will produce two more results at time unit 6. At time unit 6, you will have the value of g of x3 and g of x4, etc. So you know, afterwards, the function unit f will not have to wait for the input. The function unit f will not have to wait for the input, which is actually the output of function unit g, because just after this, the value of g of x3 and g of x4 are available, so it can start performing the operation, that is f of g of x3 and f of g of x4, etc. Clear? So it will get completed at the time unit 13. So in between 6 to 9 and 9 to 12, some other values of g will also be available. So you need to understand what, sir, in 5 minutes of time we can perform the operation on 2 values, and we actually need to perform the operation on 10 values. So 5, 5, 5, 5, 5. So 2 plus 2 plus 2 plus 2 plus 2. So 8, 13, it will get completed at 18, it will get completed at 23, and the f of g of x9 and f of g of x10 will be evaluated at time unit 28. So it is asking the minimum time required to complete this computation is how much time? So it will require at least 28 nanosecond. It will require at least 28 nanosecond. Clear? So you don't, that's the idea. Now, who asked that? Manasvi. You can draw the complete diagram, and or you can analyze it in the very first step itself, that okay, first of time I'll have to wait, but from the next step onwards, the functional unit f will not have to wait for the output to be produced by the functional unit g. Therefore, 5 time slots for 5 times 25, and for the very first time for 3 units, functional unit f will be idle. So 25 plus 3, that will be 28. Done. That's the answer. Next, question number 8. The stage delays in our 4-stage pipelines are 100, 800, 500, 400 and 300 picoseconds. Picoseconds is nothing but 10 raised to power minus 12 seconds. Now, the first stage with a delay 800 picoseconds, it is the maximum. It is the maximum delay. So you know that TP will be nothing. So maximum of the stage delay is 800. So for this fast pipeline, TP will be 800 picosecond. TP will be 800 picosecond. But, and we know that there will be wastage in the wastage of 300 picosecond in the second stage, wastage of 400 picosecond in the third stage, and wastage of 300 picosecond in the fourth stage. So for that purpose, it is actually trying to reduce this time. So it is saying the first stage with a delay 800 picosecond is replaced with a functionally equivalent design. So earlier there are 4 stages: S1, S2, S3, S4. Now this stage S1, which is taking 800 nanosecond, is replaced with a functionally equivalent design involving 2 stages. So now this S1 will be replaced by 2 stages, S1 dash and S1 double dash. Remaining will remain same. S3 will remain as it is. Oh, sorry, S2. S2 will remain as it is. S3 will remain as it is, and S4 will remain as it is. Now it is saying that the stage delay of those new stages will be 600 and 350 picoseconds. So stage delay of this will be 600. The stage delay of S1 double dash will be 350. The stage delay of S2 will be same as original because there is no change in S2, S3 and S4. So it will be 500, it will be 400, it will be 300. Yeah, sir. So for the earlier pipeline, the cycle time will be 800. For the new pipeline, cycle time will be maximum of this 5, that is 600. Maximum of this 5, that is 600. Now it is asking the throughput increase of the pipeline in percentage. Throughput is what, sir? It is asking for the increase in throughput. It is asking for the increase in throughput, that is number of tasks completed per unit of time. So what is throughput, sir? Throughput is nothing but number of tasks completed per unit time. Yes, sir. Okay. So you need to understand one thing, that for if nothing is given, nothing is being said about the stalls in the pipeline or etc. So what is the average instruction execution time in pipeline? Average instruction. What is the cycle per instruction? So the cycle per instruction will be equals to one cycle, and that will be TP. So average instruction execution time will be TP equals to 800 for the fast pipeline, because on an average each instruction will require one clock cycle. That's it. And one clock cycle is of 800 picosecond. That is the execution of each instruction will require 800 nanoseconds. So what is the number of tasks completed per unit of time? So the number of tasks completed per unit of time will be, sir, one instruction, please, one instruction in 800. Therefore, in 1 picosecond, throughput will be what? 1 upon 800 instruction. This is the throughput. In 1 picosecond, 1 upon 800 instruction, this will be the throughput. So this is the throughput of the original pipeline. Now, for the new pipeline, the throughput will be, so throughput of, I would say, throughput new will be 1 upon 600, because this time one instruction can be executed in 600 time unit. Therefore, in 1 time unit, 1 upon 600 instruction, and this is actually nothing but throughput of old. This throughput old. Now it is asking for the percentage change. Now it is asking for the throughput increase. So by what value the throughput has increased with respect to the old value? Sir, it's very simple. Its value is very simple, sir. What? Sir, change in percentage. So the new percentage or the new throughput will be 1 upon 600. New throughput will be 1 upon 600. Old throughput is 1 upon 800. So this is the change in the throughput. This is the change in the throughput with respect to old throughput, that is 1 upon 800 into 100%, because it is asking in terms of percentage. It is asking in terms of percentage. So what will it be, sir? 800 minus 600, that is 200 divided by 600 into 800 divided by 1 upon 800 into 100%. This is the value. Sir, 800 will get discounted by this. This is this. So 2 by 6. 2 by 6. So it's basically nothing but 200 by 6%. So 6 3s are 18. 33.3%. Getting the idea? 33.3% will be the answer. It is with respect to throughput. That's an aptitude problem now. So it did, the question did not ask in terms of the change in the cycle time, but it asked in terms of throughput. So I hope, is it clear to everybody? Do I need to explain it further that this is nothing but the change in throughput? Because we are looking for change in throughput with respect to old throughput. So with respect to old, you will check the percentage change. Change in throughput with respect to old throughput into 100% will be your answer, 33.33. Now, which of the following is not a form of memory? You don't know. Instruction cache is used to store the instruction. Instruction register is used to store the instruction. Instruction opcode is just a field in the instruction. It is not a form of memory. Translation locusite buffer, obviously it's a memory, but for the purpose of storing the translation information. So yeah, it's also. So the correct answer, that which one is not a memory, option C. So I hope again the same concept. Manasvi, looking at this question, you know it will not take more than 1 minute. It will not take even 1 minute. So there are some questions which will take less than 1 minute. There are some questions which will take 1 or 2 minutes. There will be some questions which will take more than 5 minutes or more than 6 minutes, 7 minutes. So that's there is a balance in the paper. Don't think that's what happens if that lengthy question comes in the exam. There will be other questions also from where you will save some time and you will apply that saved time on those lengthy questions. Okay, next, in an instruction execution pipeline, the earliest there is so much debate about this particular question. So let me try to explain the concept. If this question comes in the exam at this point of time, we can eventually challenge this, right? But in the old time, I mean, you all know that there are some questions in the GATE exam for which the data is not correct, or for which there may be more than one correct answer, right? Even if the question is not of MSQ type. So in the today's scenario, we can eventually challenge the correct answer provided by the IITs, but in the old time we could not do that. So that's fine. So if in an instruction execution pipeline, so it's a pipeline, the earliest that the data TLB access for the data, TLB, you all know, why do we use translation look aside buffer? We use this translation look aside buffer to convert the logical address into physical address. So it's saying that the earliest we can try to convert the logical address into physical address is what? So before effective address calculation has started. So please try to understand. In the instruction, let's assume if I write it like this, add R0 200 and yeah, at the rate 300, and this at the rate is nothing but memory address. This is nothing but memory address. You all know that these addresses are the logical addresses. These addresses are the logical addresses. So the idea is that we will try to get the physical address corresponding to this logical address 200. We will try to fetch the physical address based on this logical address 200 only when we have this logical address 200. Only when we have this logical address 200. So obviously we cannot start before effective address calculation has started, because first we need to start the effective address calculation. Once we know this address 200, then only we will get to fetch the data from the memory, or we will eventually translate this logical address 200 into physical address, and then from that physical address we'll eventually fetch the data. But this is an indirect address. So what will happen? This is an indirect address, so there will be multiple addresses. There will be an address 300. At address 300, you will get the effective address, right? Whatever it is, and that at that particular effective address, you will get the data. This is indirect. This is indirect. In the direct, obviously, you will start accessing the TLB only when you have completed the process of effective address calculation, right? So after effective address calculation has completed is the right answer. In one sense it will be the right answer, because once you know that the effective address is 200, which is our logical address, then you will search for the physical address corresponding to this logical address 200. But first you will have to identify this effective address, right? That's one thing. But if the addressing mode is indirect, then first you will get this address 300. From that address, you will get another effective address that will also be a logical address. When you get that logical address, which is your effective address, then you will convert that logical address into physical address, and then you will fetch the data. So the idea is quite simple, that if it is direct address, then you will start the accessing of data TLB only after getting the logical address. But if it is an indirect addressing mode, you will eventually perform two memory access. One memory access will be to access the effective address. That means when you are trying to access this effective address, another memory access is involved in order to access in order to translate this 300 into physical address, you may access the TLB. You may access the TLB. That is, you may also access the TLB during the effective address calculation. You may also access the TLB during the effective address calculation. So both of them are correct, but if somebody says the earliest possible thing, so the earliest you can access the data TLB is during the effective address calculation. Therefore, the correct answer for this will be option B. Okay. Otherwise, they must specify the addressing mode also. Clear? Okay. Let's move to the next question. This is again a very easy question related to concept of tag, set offset and word offset. Consider a computer with a 4-way set associative mapped cache. So it's a 4-way set associative mapped cache of the following characteristic. So what is the total size of main memory? Look at this. Physical address is of, so please do it in this way so that it will be easier to understand. We know that the physical address itself is divided into 3 parts. One will be tag, another will be set offset, and another will be word offset. So there is a memory of 1 megabyte, word size of 1 byte, that's fine. Therefore, it will be a 20-bit physical address. Out of those 20-bit physical address, the block size is of 128 word. To identify one word out of 128, word offset will require 7 bits. That's okay. Now the cache size is 8 kilobytes. So please, what will be the number of cache lines? Number of cache lines will be cache size divided by block size. Yes, sir. Good enough. So what is the cache size? So the cache size is 8 kilobyte and the block size is of 128 word. Each word is of 1 byte, that is 128 byte. So 8k is nothing but 2 raised power 13 byte. This is 2 raised power 7 byte. 776 2 raised power 6 bytes. So sorry, 2 raised power 6 byte will get cancelled out. So 2 raised power 6 cache lines. If somebody asks me number of sets is nothing but the number of cache lines n divided by the number of cache lines in each set, that is associativity, right? So n by p. So the value of n is 2 raised power 6. Value of p is 4-way set associative 4. So this is 2 raised power 6 divided by, did I do something wrong? 10. 1 megabyte of main memory, a word size of 1 byte. Word size of 1 byte, block size of 128. Yes, so that's okay. So 2 raised power 6 divided by 2 raised power 2 will be 2 raised power 4. So out of 2 raised power 4 sets, to identify one set uniquely, you will require 4 bits, and 7, 4, 11, you are left with 9. So the correct answer will be 947. Correct answer will be 947. Good enough. Simple question. Physical address needs to be divided into word offset, set offset and tag. 947. Next question. Consider a computer, similar type of, the characteristic of the question is exactly same. Please try to understand. Consider a computer with 4-way set associative mapped cache of the following characteristic. It's the same question, the common data question actually. So first of all, we know how many bits will be there for tag, how many bits will be there for set offset, how many bits will be there for word offset. Now it is saying a total of same thing. While accessing the memory location, so this is your location. This is your location. This H represents what? Hexadecimal. So the value is 0, C, 7, 9, 5 in hexa. Right? So how do we denote 0? So 0 will become 0, 0, 0, 0. C is 12. C is 12. 1, 1, 0, 0. This is 0, 1, 1, 1. 9 is 1, 0, 0, 1. 5 is 0, 1, 0, 1. So this is the address. This is the address. The content of the tag field of the corresponding cache line. We all know that the content of tag field will be 9 bits starting from the beginning. Content of the tag field will be 9 bits starting from the beginning. So 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0. That's your answer. That's a nahi, Satish, you are giving the answer of the previous question. Yeah, you must be giving the answer for the previous question. But this is a common data question. Here you will know that the tag field is of 9-bit. So here you can directly assign this starting 9-bit as a tag. The next 4-bit will be used for set offset. This remaining 7 bits will be used for word offset. Clear in the address. So tag field of the corresponding thing. Next one. Oh, please, it will take a lot of time. This particular question will take a lot of time because why? Let me tell you. In the old time, there was a concept of common data question. So it is a common data question. There are 3 questions associated with this data, question number 13, 14 and 15. So ultimately, each part of the common data question will be of 2 marks. So basically, these are 6 marks. So even if you spend 10 to 12 minutes in order to understand the question, the time is paid off if you are eventually able to score this 6 marks. So please don't think again same doubt that this type of question may take a lot of time, but this type of question will not come, or I mean the question of which is of that much length will not come in the today's scenario. Such questions are used to come when there was a concept of common data question, that by analyzing one particular information you may score 4 to 6 marks. You may score 4 to 6 marks. So let's look at the question, and this is a very good question. So शुरू करते हैं. Consider a machine with a two-way set associative data cache of size 64 kilobytes and block size 16 bytes. तो मैं कुछ चीजें यहीं कर ले रहा हूँ. 64 kilobyte ये हमको काम आएंगी सारी चीजें. We will require them. 64 kilobyte is the cache size and 16 byte is the block size. So this is nothing but 2 raised power 16 divided by 2 raised power 4. That is 2 raised power 12. Number of cache lines. This is the number of cache lines. So what will be value of S? Number of sets. Number of sets will be n by p. We know number of cache lines are 2 raised power 12. And the value of p is given as two-way set associative. Therefore, there will be 2 raised power 11 sets. There will be 2 raised power 11 sets. Okay, sir. That information is known to us. The cache is managed using 32-bit virtual address. Okay, so that's a new information. That generally we do what? We will have a physical address. We will have a physical address. That physical address will be translated into your word offset, set offset, and tag. But this time something else is being done. That the translation is not with respect to physical address, but this is virtually tagged cache. What type of cache is this? Virtually tagged cache. You can have two types of cache: physically tagged cache and virtually tagged cache. Physically tagged cache means the tags will be available based on the physical address, but in the virtually tagged cache, the tags will be available with respect to virtual address. So basically, यहाँ पर in this particular scenario, the information of tag will be with respect to this 32-bit virtual address, or you say it logical address. So out of those logical address, how many bits? So first of all, obviously word offset, the block size is of 16 byte. Therefore, 4 bits will go into the word offset. Number of sets are 2 raised power 11. Therefore, this set offset will be of 11 bit. Set offset will be of 11 bit, and this is your tag. Clear? So sir, how many bits are gone? Sir, 15 bits are gone out of 32. So we are left with 17-bit tag. But this tag is with respect to logical address. This tag is with respect to logical address. Why am I doing this? All these questions are this 13, 14, 15. All these 3 questions are based on this particular information only. Okay. Now, the page size is of 4 kilobyte, whatever. Page size is of 4 kilobyte. So please try to understand page size. Okay. Let's 32-bit logical address. Page size Page size 4 kilobyte. Yeah, 4 KB. Page size 4 KB. So, therefore, number of pages in the logical address space will be how many? So, number of pages will be logical address space divided by page size. Logical address space is nothing but 2 raised power 32 byte divided by page size is 4 kilobyte. So, 2 raised power 20, that is 1 mega pages will be there. 1 mega pages will be there. So, for 1 mega pages, what will be the page number? Sir, therefore, number of bits in page number will be equals to 20. So, there are 1 mega pages, that is 2 raised power 20 pages. To identify one page uniquely, 20 bits will be required. To identify one page uniquely, 20 bits will be required. Whatever, that information is not needed in the question. What is needed? A program to be run on this machine begins as follow. So, we are having a two-dimensional array of double. The name of the array is ARR. The name of the array is ARR. Now, the size of the array is 1024 cross 1024. Size of the array is 1024 cross 1024. Now, what does it do? So, it is initializing the array elements to 00. It is initializing the array elements to 00. That is, starting from A00 equals to 0.0 to A1023, it will store 0.0. Yeah, because it is less than. It is less than. So, it's initializing this, and for that particular purpose, this code is being used. Right? Please look at this. It is initializing I comma j. It is initializing I comma j. So, first of all, the value of I will be 0. The value of j will increase from 0 to 1023. So, what will happen? So, first of all, it will update A00. Then, it will update A01. Yes or no? Because the value of j will change. So, it will update up to A01023. After that, it will update A10. So, again, I value will start from 1 and j will repeat itself from 0 to 1023. So, then A12, etc. So, it will keep continuing. It will keep continuing. This is how it is being stored. Now, also given the size of the double is 4 byte. Integer is of 4 byte, size of the double is 8 byte. Array ARR is located in the memory starting at the beginning of the virtual page this. Oh, why do we need this page number? So, let's look at this. Sir, page number is 44444. It's an hexadecimal. It is in hexadecimal. So, these are 20 bits of your page number. These are nothing but 20 bits of your page number. So, again, sir, what is hexadecimal? F000. So, the page number is F value is 1111, then 1111, then remaining are 0000, 0000, 0000. And starting means, starting of that particular page means left bits, remaining bits are 0. Remaining bits are 0. So, the very first cell of this page will be 00. How many bits will be there? Sir, they will be from 00000 to 111111. How many bits? Sir, these are 12 bits. Why? Because the size of the page is 4 kilobyte. So, for 12 kilobyte, 4 bits. Leave it. It's just an information. Now, and stored in a row major order by default. How do we store the array? Sir, by default, we store the array in a row major order. Okay. What else do we understand? Sir, the size of each array element is 8 byte. The size of each array element is 8 byte. And the total size of the block is 16 byte. That means in one block, we can store only 2 array elements. Yes or no? Block size equals to 16 byte. Element size is equals to 8 byte. What does it mean? That is 2 elements in one block. Good enough. Right? Now what will happen? We will try to analyze this. We will try to analyze everything in this particular question, because 3 questions are there, and more importantly, these are 3 questions, but a single question can be framed from the concept of this particular thing. So what will happen? Sir, let's look at the memory. Sir, these are the 17 bits of tag. These are the 17 bits of tag. These 17 bits of this 32-bit physical or logical address. 17 bits of this 32-bit logical address will define that what is the tag field corresponding to this particular set. So 4, 4, 8, 4, 3, 12, 16, 17. These bits will define the block number. These bits will define the main memory block number. That's again another information. Now, then it says it is stored in row major order. It is stored in row major order. So if I just tell you one thing, that okay, it's nothing more, but this is your cache. This is your cache. Then whatever the set is, so what will be the set? So the remaining bits are 0, yes? Remaining 11 bits are 0. So obviously it will go in the set 0. Obviously it will go in the set 0. So this is your set 0. This is your set 1. Within each set you will have 2 cache lines. Why? Because it is two-way set associative. It is two-way set associative. So within each set you will have 2 cache lines. Right? Now in one set, so this particular array element, so it is stored at set 0, and within this set 0, word offset will also be 0, 0. So here we will store the information of A00, 2 elements in one cache line, A00 and A01, row major. So first of all we will store all the rows, A00 and A01, etc. Clear? Now what will happen? Sir, next element will be placed where? Next element will be placed where? So this will become 1. After this 7 bits, please try to understand. Please try to understand. You are storing 16 byte of information. You are storing 16 byte of information, that is this. So in one cache line, you will store this 16 byte of information. That is, after this 4 bytes, using this 4 byte, you can store 16 byte of information. So 0000 will be address of A00 actually, and 1000 will be address of A01 within this cache line, and after that the next address will become 10000. So this will go in the set 1. This will go in the set 1. Automatically the next element A02 and A03 will be stored in set 1. Similarly, A4 and A5 will be stored in set 2. A4 and A5 will be stored in set 2. Now my question is, that's okay that it is being done, and it is saying that initially cache is empty. Yes, we are assuming that this cache is initially empty. This cache is initially empty. Now what will happen? The only data memory references are made to the program are those to the array elements. That means your processor is only generating the addresses for the data corresponding to the elements of this array. In between, that means in between, nobody will come and change the content of this cache. In between, nobody will come and change the content of this cache. Now it is asking, what will be the cache hit ratio for the initialization loop? So this is your initialization loop. Before you initialize all these array elements to 0, 0, what will be the cache hit rate? So please try to understand. First of all, you will access A00. For that, it will be a miss. Then when you will try to access A01, because of A00, you have already brought A01 into this particular cache line, therefore it will be a hit. Then again, with respect to A02, it will be a miss, because initially when cache is empty, it will not be present in the cache. Next, when it will try to access A03, it will be a hit. So you know, out of all references, for the one reference, it will be a hit. For the next reference, for the first reference, it will be a miss. For next, it will be a hit. Then again miss, then again hit, then again miss, then again hit. So you know that for 50% 50% of them it will be a miss, and for 50% of them it will be a hit. Therefore, what will be the overall hit rate? What will be overall hit rate? 50%. Is this clear to everybody? That once you understand the architecture, you will come to know that yes, for A00, because it is not in the memory, it will be a miss. But because we are trying to bring A00 into the cache, two array elements will come, because the block size of 16 bytes, a complete block needs to be transferred from main memory to cache. So 16 byte of information will come. It is stored in row major order. Therefore, when A00 comes into the cache, along with that A01 will also come into the cache. So for A00 it will be a miss in the cache, but for A01 it will be a hit in the cache. For A01 it will be a hit in the cache. So yes, obviously the correct answer will be 50%. Alternatively, there will be hit and miss. There will be miss and hit. Clear? So that's it. So that's the very first question, that how the data will be accessed. Okay, done. The next question is, which of the following array element has the same cache index as A00? Cache index means, so this time the cache is indexed based on the set offset value. Cache is indexed based on the set offset value. Please try to understand. In direct mapping, in fully associative mapping, there's a question, if you guys remember, in fully associative mapping, no index. No index. In direct mapping, indexing will be based on line number. There is an extra information. Indexing is based on line number. In set associative mapping, the indexing will be based on set number, that is set offset. Now, what is the meaning of this question? This question is asking that which of this following array elements will have the same set offset, as the set offset of array element 00. You all know that the set offset of array element A00 is 0. This is 0. This 11 bits will represent 0. The set offset of array element 00 is 0. Now, first two element will be in set 0, next two element will be in set 1, next two element will be in set 2, right? So it works in the in the circular manner. So this is the last set. Overall number of sets are 2 raised power 11. So starting from 0, the last set number will be 2 raised power 11 minus 1. Ultimately, what will happen? In one set there will be 2 array elements, in the next set there will be 2 array elements, in the 2 raised power 11 minus 1 number set there will be 2 elements. So ultimately overall element, so cache please try to understand this. We cannot define this in terms of statement, but try to understand the concept that first of all, we will fill one cache line of each set. First, we will fill one cache line of each set. Clear? Now, what else you know? Each cache line requires 2 array elements. Each cache line requires 2 array elements. Therefore, to fill one cache line of each of 2 raised power 11 sets, number of array elements needed will be equals to, sir, in one cache line you are filling 2 elements, and there are overall 2 raised power 11 cache lines you need to fill, one from each set. Therefore, it will be 2 raised power 12 array elements. 2 raised power 12 means, let's look at this. 4 into 1024 array elements. 4 into 1024 array elements. Please. Sir, what is the array in row major order? What is the structure of array? Sir, we will have A00 to A0 1023. These are the 1024 elements. So in one row of array, there will be 1024 elements. In the another row, there will be, this will start from A1, 0 to A1, 1023. So these are again 1024. So similarly, you will have A20 to A2, 3. These are again 1024. Then again A30 to some 2. These are again 1024. So these are nothing but 4 into 1024 element. While you are accessing these elements, while you are accessing this 4 into 1024 elements, you will only be filling only one cache line of each set. But the moment you will try to access this array element A 4, 0, you will again have to go back to set 0. You will again have to go back to set 0. In this second cache line of set 0, you will store A4, 0 and A4, 1. Got the idea? So which of this 4 element will have the same set offset as A00? Sir, A4, 0. A4, 0. Along with that, A4, 1 will have the same index, because this both the elements A4, 0 and A4, 1 are in the same set. A4, 0 and A4, 1 are in the same set. Sir, next one will be what? So please let me explain. Sir, first of all, whatever the set offset of A00 will be same as the set offset of A40. It will be same as the set offset of A80. It will be same as the set offset of A12, etc. So after 4, it will keep repeating the set number. So after 1024, that is, these are nothing but 4096 element. So after every 4096 element, the next element will come into the same set. The next element will come into the same set. Clear? So that's the idea. This is the understanding which you need to develop when you are trying to solve these questions. I mean, actually this question is very important from the learning point of view. This gives you so many information that how do you analyze the information which is present in the cache memory. The last one is also very simple. The total size of the tags in the cache directory. What do we know? Sir, total size of the tag will be what? Total size of the tag. With corresponding to each cache line, we need to maintain this tag. Corresponding to each cache line, we need to maintain the tag. So what will it be? Sir, number of bits in tag. Number of bits in tag field multiply by number of cache lines. This is fixed. This is fixed. Whatever the mapping technique is, for each cache line, you will eventually store tag. So the only difference is in fully associative mapping, number of bits in the tag field will be more. In direct mapping, the number of bits in the tag field will be minimum. In set associative, the number of bits in the tag field will be moderate. Clear? So this is same number of bits. So how many bits are there in the tag field? I just told you that, sir, there will be 17 bits in each tag field, and this 17 bits are with respect to virtual address. These are virtually tagged cache. This is a virtually tagged cache. So there will be 17 bits in each tag field. And how many cache lines are there? So there are 2 raised power 12 cache lines. There are 2 raised power 12 cache lines. 2 raised power 12. So this is nothing but 17 into, this is nothing but 4 into 1k bits. So what will it be? So 34, 35, 68. So 68 kilobits, option D. 68, this is nothing but 17 4s are 68. This is 1k. These are bits. So 68 kilobits. Good enough. Next. Okay, this is a concept which is related to the concept of multi-level cache. In the multi-level cache, there are different concepts. So generally, why do we use the multi-level cache? We use the concept of multi-level cache to minimize or to reduce the miss penalty in a single level cache. If there is a single level cache, then you will try to access the data from that particular level of cache. If it is a hit, it's good enough. But if it is a miss, you will directly have to go to the main memory, and main memory is slow. So we use multiple levels of cache. So if I just define you the structure, this is CPU. Oh, if I just define the structure, you will have something like this is your CPU. Then you will have an L1 cache, then you may have some other level cache, then you will have L3 cache, and in the end you will have main memory. In the end you will have main memory. Now it is saying, please, inclusion. What is inclusion? Sir, inclusion means that whatever block numbers are present in level 1 cache, they should also be present in level 2 cache. So whatever is present in L1 should also be present in L2. That is, the blocks of L1 must be included in blocks of L2. Blocks of L2 must be included in L3. When we talk about main memory includes all the blocks of this cache, because ultimately the information will come into the cache from the main memory. Information will come into the cache from main memory. Now, this is more detailed analysis when we will go in the multi-level cache, but for this question just try to understand. For inclusion to hold between two cache levels L1 and L2. So inclusion holds between L1 and L2 means whatever main memory block numbers are present in L1, they should also be present in L2. For this to happen, which of the following is necessary? Which of the following are necessary? That L1 must be a write-through cache. Write-through cache says that whenever we are writing into the L1, we will also write into the L2. No, that's a very big misconception, and you will eventually find this answer as, the statement 1 is correct at most of the places, but this is wrong. This is wrong. Inclusion does not tell you that the content of L1 should be subset of content of L2. No, the block number must be same. That if block Bx is present in L1, then block Bx must also be present in L1. The content of block B1, content of block Bx in level 1 and content of block Bx in level 2 need not be same. Content need not be same. Content need not be same. If you say content is also same, then it becomes value inclusion. If you try to ensure that content is also same, then it becomes value inclusion. No, it is only saying about the inclusion to hold between two cache. Whatever block number is available in L1 cache should also be present in L2 cache. That's the idea. L2 must be write through. No, none of them should be write through. That's fine. The associativity of L2 must be greater than the associativity of L1. Must be greater. No sir, they may also be equal. They may also be equal. So this is also wrong. But please try to understand that if L1 cache stores 4 blocks, some blocks Bx, By, Bz, and let's assume Ba. So this 4 blocks, if these 4 blocks are present in L1 cache, then this 4 blocks must also be present in L1 cache. And to store this 4 blocks into L2 cache as well, the size of L2 cache should be at least as large as of L1 cache. Otherwise, if the capacity of L1 cache is of 4 blocks and the capacity of L2 cache is only 2 blocks, then how will you ensure that all the 4 blocks which are present in L1 cache are also present in L2 cache? So this is the only requirement for inclusion to hold. This is the only requirement, that the size of L2 cache should be at least as large as the size of L1 cache, so that you can store all the blocks in the L1 as well as in L2. So the only correct statement is statement 4. The general misconception is with respect to 1. Therefore, to confuse you, 1 and 4 is also given, but the correct statement is only option A. Correct answer is only option A. Okay, let's look at this next question. I guess we are extending it, but cannot do anything. I already told you that there are many questions in this particular chapter. So in the COA, if at all you can expect a question, then definitely there will be 2 questions from COA, one from memory organization, another from pipeline. So we cannot ignore it. So a file system uses an in-memory cache to cache disk blocks. This is a lovely line. Generally, the moment you read cache, you understand that there's a CPU, there's a main memory, and in between there's a cache memory. No sir, cache is just a normal name which is used to store the data temporarily. So when we are talking about file system, then the files are by default stored in the disk blocks of the secondary memory, right? Files are stored in the disk. So when you are trying to access the files of our file system, you will eventually bring those blocks of the disk into the memory, and from memory CPU will access them. So for the temporary purpose, you are storing the blocks of the disk corresponding to a file in the memory. Therefore it says in memory cache. In memory cache means you are caching the blocks of disk. You are caching the blocks of disk into this memory. There is no concept of cache involved in this question. No concept of cache involved in this question. For the purpose of caching, we are using the main memory. For the purpose of caching, we are using the main memory. So when we say cache size, it's actually nothing but main memory size. When we say cache size, it's actually the main memory size, and there we are storing the information. Now it says the miss rate of the cache is shown in the figure. It says that as the cache size increases, miss rate is decreasing. As the cache size increases, miss rate is decreasing, and it means hit rate is increasing. Now it says the latency to read a block from the cache, that is from main memory, is 1 millisecond, and the latency to read a block from the disk is 10 millisecond. Okay, if the data is present in the main memory, you can read it in the 1 millisecond itself. If the data is present in the secondary memory, you will require 10 millisecond. Assume that the cost of checking whether a block exists in the cache is negligible. That means that searching time that you will require to check whether the block is present in the main memory or not, it is given as negligible. Available cache size is multiple of 10. That is, your size of the memory is in the multiple of 10. You cannot have a 25 megabyte cache. Either you have 20 megabyte cache or 30 megabyte cache or 40 megabyte cache. You cannot have 25, 35, 45, etc. Now, the smallest cache size required to ensure the average read latency of 6 milliseconds. The average read latency of less than 6 milliseconds. That is, the average time to read must be less than 6 milliseconds. So forget about this size. Just think in terms of hit rate. That what is the average access time? T average for read, let me write, T average for read will be nothing but, so the average, if you will check for the data in the hit, if it is a hit in the cache, then you will read it from the cache, and reading from the cache will require only 1 millisecond. Reading from the cache will require only 1 millisecond. Or If it is a miss in the cache, then it will be a miss with rate 1 minus h. Let me write capital H. If it is a miss in the cache, then it will be miss in the cache with rate 1 minus h. In that particular case, how much time will be required? First of all, you will bring the block from secondary memory, or that is from disk to main memory. That will require 10 millisecond, and after that, to access that block from the cache, you will eventually require 1 millisecond. So that's the idea. This is the overall thing. So this is your average access time, and the question is saying that this average access time should be less than 6 milliseconds. So whatever this value is your average access time. It should be less than 6 milliseconds. It should be less than 6 milliseconds. So we just need to calculate the value of hit rate. What will it be? Sir, h millisecond, or let me just write h millisecond is a plus 11 minus, so this is 10 plus 11 minus, this will be minus 11, h should be less than 6 millisecond. Okay, sir. So minus 11h plus h will be 10h. So 10h should be greater than or equals to 4. 11 minus 6 will be 5. 11 minus 6 will be 5. So 10h should be greater than 5. It gives you that h should be greater than or equal to 0.5. That is, hit rate should be greater than or equal to 0.5. Hit rate should be greater than or equal to 0.5 means miss rate should be less than 0.5. If miss rate is 1 minus h, so if we are saying that hit rate should be greater than or equals to 0.5, that means miss rate should be less than 0.5. Now, where is the miss rate? 0.5. That's an important thing. Sir, this 50%. 0.5 means 50%. 0.5 means 50%. That means less than 50%. Less than, in percentage it will be less than 50%. So sir, here it is percentage, 50%. So your miss rate should be lesser than this. The miss rate will be lesser than this only with respect to block sizes 30, 40, 50, 60, 70 and 80. But so if the block size is 30, 40, 50, 60 or 70 something, then the miss rate will be less than 50% and ultimately average read access time will be less than 6 milliseconds. But it is asking for what? So the question is asking for a smallest cache size. So among this possible cache size, the smallest one is this, that is 30 megabyte. The smallest one is 30 megabyte. Therefore, the correct answer for this will be 30. To ensure average read latency of 6 millisecond, the minimum size required of the cache is 30 megabyte. Minimum size required of the cache is 30 megabyte. Clear? Is this okay? What happened, Manaswi? Anything wrong? This is the average access time, normal formula for average access time. Why are you scared? Average access time, hit time plus the cache access time plus miss rate plus cache memory or the larger access time plus cache access time. This should be less than 6 milliseconds. No problem with that. Right. So if we calculate this, we'll get this value, that, yeah, this is the expression. It says that 10h or the 10 times the hit rate must be greater than 5, that is hit rate must be greater than 0.5. Ultimately, hit rate should be greater than 50%, therefore miss rate must be less than 50%. Clear? That's it. Next one, question number 18. These are the very easy questions. These two are the very easy questions. The width of the physical address on a machine. So we know that what is the width of the physical address. So it is given as your physical address is of 40 bit. Okay, sir. The width of the tag field in a 512 kilobyte 8-way set associative cache is, okay, 512 kilobyte 8-way set associative cache. It is asking for tag. It is asking for number of bits in the tag. So please, the block size is not given. Block size is not given. So let's assume that to represent a block, X bits are required. Let's assume this, that to represent a block, X bits are required. So if X bits are required, then the block size is equals to 2 raised power X. Block size will be 2 raised power X byte. If this is the scenario, then what do we know? Number of cache lines will be how many? Number of cache lines will be cache size divided by block size. Cache size divided by block size. So sir, how many, what is the cache size? So the cache size is 512 kilobyte. And so the block size is 2 raised power X byte. So this 2 raised power 9. So this will eventually be 2 raised power 9 minus X is the number of cache line. 2 raised power 9 minus X is the number of cache line. I hope you understand this. This is nothing but cache size divided by block size. I am saying if X bits are required, for word offset, then obviously block size will be 2 raised power X byte. So if the block size is 2 raised power X byte, then it's a kilobyte. Kilobyte. I made a mistake. This will be 19. 512 kilobyte, not 512 byte. So it will be 2 raised power 19 minus X. Okay, sir. So how many sets will be there? Number of sets will be now n by p, that is number of cache lines divided by p. Number of cache lines are nothing but 2 raised power 19 minus X, and the value of p is given as 8. So it will be nothing but 2 raised power 19 minus X, and this 8 is actually nothing but 2 raised power 3. So this 3 will also get subtracted. So sir, the number of bits in the set offset will be what? Sir, if there are 2 raised power 19 minus X minus 3 sets, then the number of bits in the set offset will be 19 minus X minus 3. 19 minus X minus 3. Sir, how many bits will be there in the tag? So sir, number of bits in the tag will be 40 minus number of bits in the set offset, that is 19 minus X minus 3, minus number of bits in the word offset, that is X. Sir, what is this value? 40 minus 19. This minus will become plus X. This minus 1 will become plus 3 minus X. X got cancelled out. X is cancelled out. This becomes 43. This is actually 16. 19 minus 3, 16. So 40 minus 16 will be 24. 40 minus 16 will be 24. Clear? Is this okay? So if this is the scenario, then the number of bits in the tag field will be 24 bits. Out of 40 bits, 19 minus X minus 3 will be required for set offset, so they need to be subtracted. X bits will be required for word offset, so they also need to be subtracted. So 40 minus 19 minus X plus minus 3, whatever happened has happened, and the final result is 24. Let's look at the last question. This is the last question from memory organization. A processor can support a maximum memory of 4 GB. So 4 GB is actually what? 4 GB is 2 raised power 32 byte. Where the memory is word addressable, a word consists of 2 bytes. So this is 32 byte is the overall thing, but it is saying each cell is of 2 byte. Word addressable means each cell is of 1 word. It implies that is of 2 bytes. Therefore, number of cells in memory. How many cells will be there in the memory? So, number of cells in the memory will be total memory size divided by size of each cell. Simple concept. Total memory size divided by size of each cell will give you the number of cells. Clear? So total memory size is 4 GB and the size of each cell is given as 2 byte. So sir, what is this? 4 GB is actually nothing but 2 raised power 32 byte divided by 2 byte. So this is nothing but 2 raised power 31. So if there are 2 raised power 31 cells, if there are 2 raised power 31 cells in the memory, if there are 2 raised power 31 cells in the memory, therefore number of bits in address will be how many? The memory is cell addressable, number of bits in address will be log of base 2 of number of cells, that is this. So this will come out as 31. So minimum how many bits should be present in the address field? Minimum 13 or 13 bits should be present in the address field to address all the cells of that memory. To address all the cells of that memory. Clear? So this was the last question of memory organization. The last concept is related to the concept of DMA. It says what? Let's look at the question. Only 2 questions are there, so will not take much amount of time. For a magnetic disk with concentric circular tracks, it's obviously correct. Obviously, all the tracks has the same center in the magnetic disk. It's obviously fine. The seek latency, that is the time required to seek a particular track. The time required to seek a particular track is not linearly proportional to the seek distance. So means, what does it say? That there may be various number of tracks. So if you want to move from this track to this track, let's assume we require x times. So to move from one track to another track, you require x times. But if you want to move from one track to 10th track, why this time is not 10x? Why? In general, why this time is not 10x? Generally in the calculation we assume that this will be 10x. If the time to move from one track to another track is x, then the time required to move the 10 tracks should be 10x. But generally it does not happen. The seek latency is not linearly proportional to the seek distance because of what? Because of what? Initially your read-write head will be steady, right? So to give it some momentum, you will require some time. To give it some momentum, you will require some time, and the momentum change is known as moment of inertia. That something is at the rest. You will have to provide some extra push before it is moved. Once it has started moving, you don't need to do anything else. But once you need to stop it, again you need to provide some extra force. Again, you need to provide some extra force. Getting the idea? So that's the idea, that it does not happen in that regards because of this arm starting and stopping inertia. You need to change the moment of inertia of the arm. So once you have started from here to here, it will require same amount of time, but some extra time is required to start and stop. Therefore, to move the track from one track to another will be x, but it will not be 10x, it will be less than 10x. It will be less than 10x. Why it will be less than? Because anyway, once you only need to start and stop only once, the remaining thing can be at constant rate. Remaining things can be at constant rate. Therefore, the correct answer in regards to this will be, but you don't need to worry about this type of questions. Don't think that's what is happening. You don't need to worry about them. Why? Because such type of questions will come or appear only once in a while, and many of you may not be able to understand them. So that's okay. Last one is the concept related to DMA. Last one, this is the last question. It is related to the concept of DMA. What does it say? The size of the data count register. So I hope you all know the context of DMA controller. This is your DMAC. This is your DMA controller. There are various things. You will have one register which is known as address register. This address register contains the address of the memory location at which you need to perform the next operation. Apart from that, it also consists of a count register. So you will transfer the data from the between IO device and memory one by one. One word at a time or one byte at a time, and after transferring one byte or after exchanging one byte between those devices, you will reduce the value of count register by 1, and you will keep performing the DMA operation. You will keep performing the DMA operation until this count value becomes 0. Until this count value becomes 0. So the moment this count value becomes 0, you will stop the operation. You will stop the operation. right? So it says the size of data count register of a DMA controller is 16 bit. So it is saying, it is being said that this count register is of 16 bit. So how many bytes can be transferred at a time? Sir, number of bytes which can be transferred are 2 raised power 16 minus 1, because this is the largest number which can be represented, 2 raised power 16 minus 1. Those many bytes can be transferred once the DMA is initialized. Now, the processor needs to transfer those many kilobytes from disk to memory. The data which we need to transfer is given, that we need to transfer those many bytes from disk to memory. Now, it is also being said that the memory is byte addressable. What does it mean? If it says that memory is byte addressable, I'll explain that. We'll talk about that in a while. Yeah, if your option is D, I'll explain in a while. So, the processor needs to transfer a file of that much amount of size and the memory is byte addressable. That means we will transfer only 1 byte of information and will reduce the value of count. So, only how many bytes can be transferred? 2 raised power 16 minus 1, that is 2 raised power 16 minus 1 bytes can be transferred. Once the DMA is initialized. Once the DMA is initialized, you can transfer only 2 raised power 16 minus 1 byte. And apart from that, it says the minimum, it is asking that minimum number of times the DMA controller needs to get the control of the system bus. That is, minimum number of times we need to initialize this DMA will be how much? Sir, it will be nothing but the ceiling function of what? Sir, we need to transfer 29,154 kilobytes of data, but in one go we can transfer only 2 raised power 16 minus 1 bytes of data. So the number of times we need to gain the control of the system bus, or the number of times we need to initialize, we need to initialize the DMA will be given by this. Let me evaluate this value. So it will be nothing but 29154 into 1024. Whatever, this is very large number, but 29853,696 divided by 2 raised power 16 is nothing but 64 into 1024 minus 1. There will be 65535. What is this value? 29853696 divided by 65535. This comes out as 455.53. So after gaining the control of the system bus 455 times, you will be left with some amount of data. And to transfer that remaining data, you will have to access the DMA 456th time. Therefore, the final answer will be 456. The number of times clear hai? The number of times we will have to gain the control of the system bus is 456 times. Clear? That will be all. So guys, if you guys want to stay connected, अगर आपको चाहिए है कि मैं क्या और आपकी हेल्प कर सकता हूँ, like I can provide you with the different questions, PPT, PDFs of all the sessions which are being conducted on YouTube or free app, or the sessions which are being conducted as free app classes. If you want the PDF of all those sessions, then I'll start sharing those PDFs and the important questions on my Telegram channel from now on. So you guys can join this Telegram channel and stay connected for all the future updates. So this is the link to access access the Telegram group, and you can also search by CS by Vishal Rawatia. You will get this group. Do join this particular group so that you will get the updates regularly. related to these sessions, and you will also get the PDFs related to this particular thing. Pushpak Jyoti, which class take in paid class? Pushpak, soon I am going to start, like, I don't know exact date, but yeah, the next subject which I'll teach in the paid class will be discrete mathematics. When it will start exactly, the date is yet to be confirmed, but in the crash course I'm going to start the database management system in the month of, or in the first or second week of September itself. So that's the idea. The next subject which I'll teach in the paid class is going to be discrete mathematics. Soon you will get the dates for those particular sessions. In the crash course, I'll start with the database management system, and for free app classes and free YouTube classes, just join the Telegram group so that you will get the updates related to that. So that will be all for this particular video. Thank you very much. I hope you have learned something new in this particular session and you are able to realize that COA is not that difficult. You just need to understand the theoretical concept behind all the statements and you will be good to go. So that will be all. Thank you very much. If you are new to the channel, then subscribe for the channel and press the bell icon so that you will get the notification about such wonderful videos. That will be all. See you tomorrow. Take care.